Yeah, thank you very much for the introduction, and welcome back, everyone. So this morning, my colleague Emanuel already introduced our DLR swarm navigation system, which is a system that tries to provide means of communications, localization, and also time synchronization with one system. So let's directly go back to the experiments and go to the volcano Mount Etna on Sicily. So Armin from DLR Robotics this morning already talked about the Arches mission, and he basically gave you the robotics perspective. And now I want to give you more the radio localization perspective. So again, that was the experiment area. And for radio localization, that was basically the setup. So we had a radio node in the lander. Then we had several payload boxes with the radio nodes. Shown here are 3. In total, we had 7. And then we had 2 rovers that we call Vespucci and Diaz. And all of these nodes are capable of performing ranging. And that means we can get distance estimates among all of them. The rover Diaz was special. He was equipped with a 4-port phase coherent transceiver and a 4-port multi-mode antenna, which allowed us to not only perform ranging, but also get direction of arrival information from incoming radio signals. So let's start with the ranging. In theory, what you often see is a model like this. You assume Gaussian noise with a certain variance and 0 mean. However, in practice, and now this is actually measurement data from Mount Etna, this looks a little bit different. So first of all of these agents seem to have a certain ranging bias, which is apparently constant, at least over the time of this measurement duration. And if you dig a bit deeper, now here's the ranging error from the rover Diaz, depending on the direction of arrival, then we see, okay, actually it's not constant. It also depends on the direction where the signal is coming from. So this is a consequence of the antenna and also the complex electromagnetic interactions of the antenna and the surrounding rover. So first, we realized that in order to be able to do accurate ranging, we must estimate and compensate these biases. So next, let's have a look at direction of arrival estimation. Again, in theory, you have a certain model how your antenna behaves. So here you see the phase pattern of this antenna. And actually, this is not purely from theory, it's already measured in a measurement chamber. But then in practice on the rover, the antenna behaves a little bit differently. Now you might say, well, this looks quite similar. However, these small differences here between the assumed and the actual antenna model lead to biased direction of arrival estimates. Again, if you don't want to have that, if you want to have accurate direction of arrival estimation, antenna calibration is vital. And here I want to also stress the point that it's not sufficient to do this once before the mission. For instance, as Professor Yoshida talked about this morning, we might have reconfigurable robots, or we might have robots which can pick up and carry boxes. Now, all of these reconfigurations, boxes, they would have an impact on the antenna characteristic and thus on the direction of arrival estimation and also on the ranging. So our take at this is simultaneous localization and calibration. So that's basically how we tackle one of the challenges that Raj mentioned this morning, the calibration aspect. So simultaneously, we localize the robots in terms of position and orientation, and we calibrate direction-dependent ranging biases and also antenna responses. If you're interested in the technical details, please have a look at the papers or feel free to approach me in the lunch break. Instead, I want to show you how this looks in practice. So on the top left, you see a map. The ground truth is in black, and in colors, you will see the estimated trajectories. Top right, you will see the estimated direction-dependent ranging bias of the rover Diaz. Bottom right, you see the estimated phase pattern on the rover dias. So we estimate in the background many more things, also the ranging biases of the other boxes and rovers, but here in the video, we show only that. So now when the rovers start moving, we realize, okay, first of all, well, our antenna response is not quite as we thought before. It's a little bit different. Same for the ranging bias. And very shortly, we get stable estimates. So the algorithm has converged. We also realized for the ranging bias, for instance, this is like -1 meter, but with several decimeters difference depending on the DOA. So this is really something we should estimate and compensate if we want to get high accuracy. So that was basically the first part of this experiment, where the robots were moving close to the lander area, and we did simultaneous localization and calibration. And now that the radio localization is well calibrated, we feel more confident, so the rovers can go to a distant area of interest. And as you can see here, again, the ground truth is in black. Arrows get a little bit larger there, but we should really stress that this is a very challenging geometry for radio localization. So the rovers are very far apart from the anchors. All the anchors are in one direction. And ultimately, the rover Vespucci, shown in orange here, is so far away that he's only localized through a relay through the other rover dias. So yeah, not going into the actual numbers here, but two things are interesting. First of all, we compare non-cooperative and cooperative localization, where non-cooperative means we exchange only signals between anchors and the robots, and for cooperative, also the robots communicate with each other. And clearly, the cooperative outperform the non-cooperative approaches. Furthermore, we have seen that simultaneous localization really helps to get better accuracy and outperforms state-of-the-art approaches. And before I talked about single link localization, to show that this really works in practice. So again, single link localization is only possible because dias can not only perform ranging, but it can also estimate directions of arrival of the radio signals, and thereby it can act as a localization relay for Vespucci. And to prove that this really works, we did it for the entire experiment. As you can see here with a dashed line, and we see, okay, we can really localize Vespucci only through dias. We get a little bit worse, but this works. So to conclude this talk, I've shown you a bit the DLR swarm navigation system and our demonstration within the Arches space analog mission. Specifically, I've shown that single link localization is feasible, and that by simultaneous localization and calibration, we can estimate and compensate biases and thereby greatly improve the localization accuracy. Thank you very much.
Thank you very much. So is there any question in the audience?
Thank you for the interesting talk. I was not aware of this high complexity due to the signal effects there. How would this behave in an area with multiple reflections of radio signals, like a forest or something? Do you think it is feasible deploying it to an area like that?
Very good question. So in the end, we call that multipath propagation. So signals that are reflected or scattered at other entities. That means at the receiver, we get an overlaid bunch of signals coming from wherever. So fortunately, an environment like this on Mount Etna, but also like what we would see on a moon or on the Mars, is rather favorable. So there's not that many reflectors around. However, what we see here, for instance, we saw signals being reflected at the lander, but there is in the literature, there's huge research being done on how to do radio localization with multipath propagation. So there's many algorithms to separate actually these signals, And this is also something that you can take into the account in the design of your system. So in simple words, the greater the bandwidth of your system, the better you can distinguish different signals arriving at different times. So this is, in the end, it's an engineering task, and the system must be specifically designed for the actual mission.
Is there any other question in the audience?
Thank you for the talk. That was really cool. I'm curious, maybe 2 questions if you can answer them quickly. The first one is, what information in the collaborative case were you sharing? Like, were you sharing the results from one, or were you just sharing like a range measurement, if it was just that simple? And then secondly, are you considering moving further into your Slack and adding the mapping in as well, so that you don't know where any of those beacons are, so you're simultaneously localizing yourself, them, and doing the calibration all at the same time?
Very good question. So for the first part, we are using directly the received radio signals. So you could also, in the first step, estimate time of arrival, direction of arrival, then feed this to a localization filter. We use directly the received signals because they contain all the information also about the behavior of the antenna, for instance. Right now we're using a centralized approach, but you can also make this distributed. So this is ongoing work. And for the second part of your question, so these methods, also from like the estimation theory that's behind all of this, they blend very well with, for instance, SLAM. So the similar name is not a coincidence. So you can actually integrate this. This is also something that we are working on, also with partners. For instance, here we had 2 sensor boxes that were not localized in the beginning. Then they were localized, and once they are localized, they can also, of course, help the robots when they move further on. But ultimately, of course, you can do SLAM. You can also combine it with other sensors and so on.